Hello, everyone. Rob Persons with Artisan Embedded Technologies. I'm a senior sales architect. Going to change speed a little bit here. This is an industry, rail industry, which is not looking for the fastest, quickest connectors or the fastest GPUs in the marketplace. This is very much a different type of industry, though they are actually going through some similar sort of things that the military did probably 20 years ago in the 90s when there was a transition into COTS products from proprietary designs. If you look at the rail industry today, you see a lot of existing systems out there that are still proprietary in design, and even to the point of actually having their own custom OSs. We actually had a customer we spoke to recently that were still doing their own OS designs for these things, which is mind-boggling to me. So we're actually trying to promote a new class of system within the industry, the rail industry, to try to leverage some of those experiences that we had back in helping it transition the military away from proprietary designs and start to adapt to COTS products like VME and VPX. As I mentioned, the rail industry has been around since really the 1830s. And some of the key goals within the industry itself have been to lay as much track as possible and to maximize the amount of freight that you could possibly move on the track along with people and raw materials. It's been evolving over the years. They have done a pretty good job of increasing the amount of total traffic that can actually utilize these tracks. And track utilization is money in their world. It started originally to try to maximize the use of these tracks is to use multiple trains on a single piece of track at the same time. They leveraged initially some schedules, very simple scheduling system where they had timetables and stopwatches basically to go and indicate what trains could be on a particular piece of track at any given time. In fact, the time zones that we live with now are really an outlay of the whole need to have better timing by the rail industry to be able to have a continuous or a common time throughout an entire area. Eventually, it moved away from these kind of old systems of timetables and stopwatches to more automated systems where there's actually embedded systems, sensors in the track, and then signaling devices that'll actually indicate what trains can be on a piece of track and which ones couldn't be on a piece of track. But as time progresses, it required a lot of human intervention to continue to make sure that the track utilization is proper, but also in a safe fashion. And it relies a lot on the trains, even today, still rely on people to be actually involved in making sure that the train conditions are safe. But because of the recent rail accidents that we've seen, we've actually started to see a push towards automated systems using something called positive train control. In other parts of the world, they have a different name for it. But basically, an automated way to be able to manage trains and to be able to stop that train if they're getting into dangerous situations. As you can see here is kind of diagram of what's essentially supposed to be positive train control. And in a sense, it's just giving the train situation awareness so that it knows where it is at any given time and that the network knows where it is, and to be able to make sure it's not moving itself into dangerous situations. The push, again, as I mentioned it, has been primarily due to systems where you have a mixture of freight and commuter rails. You have a lot of human errors that have caused accidents. We've seen these sorts of situations over the years where we've had people die because of improper control by an engineer or a rail condition that wasn't detected and the train moved into a bad situation. We're also seeing a lot of movement of oil out of Canada and have seen a huge number of rail accidents in the process of moving crude away from Canada into areas where that's being refined in the States. So the goal here is, back in 2007, was for Congress actually had a mandate to eliminate these kind of dangerous situations and to have the rail industry move into a more modern fail-safe type of system known as positive train control. And it was primarily focusing on Class 1 railroads that were moving hazardous materials and any piece of track that has people on it, either intercity kind of transportation or commuter rails. And we see a lot of that if you've been to New York or you've been in that Northeast corridor, you see all that mixing together. You see people, freight, and all being mixed together within the same track. The original mandate to have this all implemented was 2015, but has since been pushed to 2018. And primarily that happened because nobody got the systems in place in time. I think there was one, Amtrak had it actually in place by the end of 2015, but nobody else did that throughout this rest of the country. A large part of that issue is dealing with a special type of compute system called Failsafe Computing that basically forces, if the computer has a problem, it can actually detect that problem and shut itself down to a safe state. And this is a critical part to this entire system that's been very difficult to implement. And the part of the issue for the rail industry is they've had certain ways that they've done things over time and have struggled to actually get that implemented as part of this entire system. And that's kind of what we're here to try to do, is to help move these companies into this new type of system by actually having an off-the-shelf product, a COTS product, to actually help them with fail-safe computing. To get a certified system, you typically need to work with an organization, somebody like TÜV SÜD, who's actually kind of a partner in the process of actually having your designs analyzed. But beyond that, they actually go through and look at your design practices. They look at engineering processes. They look at manufacturing processes. So it's an entire interactive process to actually get to a point where you can actually get to a point where you're saying, I've got a SIL4 certified fail-safe computing system. Along with that, we also have to include a body of evidence, which in turn becomes actually a piece of the deliverable to our customers as well, to be able to help them in the process of getting their systems ultimately certified. Very much like you see in the telecom industry, if you're doing NEBS, or in this case, the same thing here, is you can have a platform that's NEBS compliant, but whenever you add any other additional pieces to it, you have to also get that certified. But by going and doing a COTS-based product like this, it helps them actually save time and money to actually get to that point. We've invested 4 years worth of time to get to a point where we understand the process and be able to get to a platform like that that is certified to SIL4. And we're hoping that kind of expertise will help our customers ultimately get to that same point. To get to a little bit more detail on exactly what we're doing in this situation, a traditional fail-safe computer would be using a hard lock step operation where the address data buses are synchronized. So you have a pair of master checker CPUs. You might have up to 3 CPUs in that case. There's actually a third one you could have in some systems. But the address and data buses are the things that are actually synchronizing the data, and they're actually checking each transaction, what the data looks like, and make sure that everybody agrees with that same data. And if it isn't, then the system would fail into a safe state and back up, move over to a different system. We've kind of changed the paradigm a bit, and we've actually worked with TÜV SÜD and have actually got this approved of moving that deterministic boundary down to the fabric layer. And part of the reason for doing this was it's very difficult to do a hard lock step design, and it really limits the types of processors that can actually be used in this environment. Modern processors today are very undeterministic. We've all dealt with it, and especially if you start to look at multi-core processors. So by moving the actual data checking piece of this down to the data fabric, we've actually been able to allow a lot more flexibility on the types of processors that are used for the master and the checker CPUs that we have in this situation. We still have data integrity that's actually being managed, but it's using an FPGA on these pair of boards to actually make sure that the data confirms and is good before it gets actually sent out to the data fabric to the rest of the I/O cards that are in the system. And that's what's really the main part of this fail-safe computer, or the pair of processors in here that actually do all this magic and make sure that it's operating in a safe state. On top of the processors, we're actually running VxWorks 653, which I'm sure many of you have seen from the airline industry. The AirInc 653 is actually pretty pervasive within a lot of military applications. It's a containerized partitioning operating system. The partitions can actually run a variety of different operating systems. In most cases, most of our customers are just running VxWorks or VxWorks 653 in them and have a single partition. But you can potentially have up to 256 partitions and running different types of things. And so part of that application could be a safety application while the other ones are not. Don't have to be safe. We do additional hardware or software elements to this operating system to actually give you the ability to synchronize those application tasks that are running. But the beauty of the system right now is that both of these CPU cards, the master and the checker, are identical, and they're running the same exact operating system, and they're running exactly the same code. So it's not as though you have to have sophisticated differences between your applications running on the two different sides. You're running exactly the same code, and if they match, then they work. If not, you fail over to a different system. So this is kind of a snapshot of what our control-safe platform looks like. We actually have two elements. One is an active control-safe computer and then a standby. And we really have a pair of those there interconnected through a safety relay box so that we have a high availability type system. So if you have a failure situation in the active CSC, then it will move over to the secondary CSC and keep you moving. A safe computing element inside in a rail industry means that this train stops whenever you have a failure. And so the goal here is to keep the train moving, obviously. So we do have a redundant system for our customers to actually integrate into their control systems that they have. And this, again, has been certified by TV Sud. So this is our component that we hope that we can actually promote within this industry and actually help them move along quicker to actually implement PTC and other control systems like that require a fail-safe computing element.